Hello, your team complex. Through our project, we designed a learning-based adaptive cruise control. This is our table of contents. When driving with ACC on, we frequently felt that the system tends to be dull than human driving. We wanted to make smarter ACC model using machine learning. By using sensors, each vehicle can work as a data collector which analyzes surroundings and motion itself. By using these data, we aim to build an optimal learning-based ACC model which is trained by individuals' driving habits. Our final goal is to create an algorithm to estimate optimal speed of each vehicle according to the behavior of three vehicles driving in the same lane.
In our project, we are considering three conventional machine learning methods: linear regression, random forest, and SVM regression. Initially, we can assume a linear relationship between the data, represented by the equation y equals ax plus b. In such cases, the least square method is employed to find a regression line, minimizing the distance between the line and the data points. Next, we consider random forest, an ensemble learning method using multiple decision trees. Each tree in this method is trained on a distinct subset of the data. The final prediction is an aggregate, either the average of all trees' predictions or a majority vote. Lastly, SVM, known primarily for classification, is also a viable option for regression problems. It operates by mapping data points to a higher dimensional space and identifying the optimal flat boundary for predictions within this space. We initially chose linear regression, assuming a linear relationship in our data. However, upon data visualization, it became evident that the relationship was not strictly linear. Consequently, we have added nonlinear models that better accommodate nonlinear data characteristics, such as random forest and SVM. While deep learning is powerful, it demands significant computational resources and extensive data for training. Given our project's constraints, including limited data, deep learning doesn't seem to be a feasible approach. Therefore, we've decided to employ machine learning algorithms and compare each other's performance.
Hi, I'm Minchang and I'm going to talk about data preprocessing and analysis. The dataset we chose is the NGSIM dataset. The next generation simulation dataset is a collection of traffic datasets collected by the United States Federal Highway Administration through field observations. Those are high-quality datasets with very high reliability. The NGSIM datasets include detailed information about vehicle trajectories, such as position, speed, and acceleration, recorded over a period of time. Cameras in the air recognize vehicles and display the vehicle ID for each vehicle. Among various vehicles, three vehicles that could be easily observed in the same lane were randomly selected and were called rear vehicle, equal vehicle, and front vehicle depending on the direction of movement of the vehicle. Additionally, the I-80 dataset reflects the traffic conditions in the Iowa region, and the US 101 dataset reflects the traffic conditions in the California region. The former was collected over various period of time, and the latter was collected over a specific period of time. By utilizing two data with different characteristics, data diversity was secured. Next is data preprocessing. First, we selected the features we wanted from the existing NGSIM dataset: frame ID, which provides time information, global X and global Y, which provide vehicle location information, and wave velocity, which provides vehicle speed information, were selected, and the types of vehicles were displayed differently depending on the frame ID. Next is feature scaling. Since the NGSIM dataset has a resolution of 10 frames per second, one frame, which is the interval between frames, was converted into 0.1 second. Additionally, the speed unit that was feet per second was converted to meter per second for convenience. Next is data cleaning. In order to reflect the vehicle's real-time speed information as accurately as possible, the interpolation process was not performed, and sections with outliers were excluded. In the case of data where the speed instantly becomes zero, as shown in the graph on the left, it was kept as is because it can be used as meaningful data in calculating the optimal speed of the vehicle when compared to the speed of the front and rear vehicles. However, as shown in the graph on the right, in the section where the speed of all three vehicles remained at zero, the relative speed with the front and rear vehicles continued at zero, so it was judged to be meaningless data and was excluded. Lastly, the clean data was visualized as a graph to visually check the distribution of the data and use it to understand the data and improve the model.
I'm Seungsup and I'll be introducing our results. We implemented 3 machine learning models and trained them on a pre-processed dataset of over 7,000 data points, then applied them to a novel dataset and qualitatively analyzed the results. The optimal parameters were found with grid search CB, and results were analyzed using MSE, MAE, R-squared, and cross-validation scores. The results for each model are as follows. Linear regression was fast but rather inaccurate. SVM had better accuracy but was slow in predicting the best velocity, and finally random forest had the best accuracy and prediction times. The best model was thus the random forest regressor with over 99% accuracy and a fast response time of 60 milliseconds, in compliance with the generally accepted scale of 10 milliseconds for vehicle response times. The trained models were then applied to a new dataset of vehicle data taken in a crowded intersection with multiple braking and acceleration periods. The results for each model are as follows. Both linear regression and SVM generally showed that predicted values were higher than actual values, indicating some suboptimality in human drivers. However, there were enough data points in exception to this rule for both models. The random forest model also showed that human drivers were driving slower than what is optimal based on our predictions. It also had a much better prediction rate, with predicted velocities differing by a constant value from actual velocities for predicted values over 10 meters per second. Finally, we concluded that the random forest model was the best fit for our data because its permutation importance matched with our intuitive guess that vehicle velocity is most dependent on rear vehicle velocity, followed by front vehicle velocity. Other models failed to properly find this correlation. Our project could be extended in several ways introduced below. Firstly, we could add more categorical features such as the road geometry, weather conditions, and heading data. Secondly, we could extend our model further to predict vehicle velocities for congested intersections where the vehicles are stationary or moving very slowly. Our current model's predictions result in polynomial residuals for velocities of 0 to 10 meters per second in case of acceleration and braking scenarios. Lastly, given a longer time duration, we can compare our model's predictions with deep learning models such as LSTM. It was undesirable to implement an LSTM model for our dataset due to the time sequence being very short, about 1000 frames or 10 seconds per subset. In conclusion, our random forest regression model accurately predicted the optimal vehicle velocity based on front and rear vehicle information and pinpointed improvements in human driving behavior. Thank you.